This is tutorial number 13, the equation of motion for free convection near a hot vertical plate for incompressible flow with constant property are listing below. So we have a 3 equation here. So I think the equation number 1 here is quite familiar. It is the continuity equation. So and then we need to do the dimensionless analysis for all these 3 parameters. So we have the dimensionless variable here. So as listing in this table, and in exam, if the dimensionless analysis question like this comes out, so I will give you the dimensionless variable like this one. So and then again, please be careful. Sometimes in question, I will give you the kinematic viscosity, because the kinematic viscosity, the symbol is like this. Okay, so this is our handwritten. So but handwritten style, but this is the type style. So sometimes people's students confused with a velocity. Okay, please. So velocity, normally we will use a common v, a common small v. Okay. So I think you already know that viscosity has 2 types. So it has kinematic viscosity and dynamic viscosity. So mu is the dynamic viscosity. Okay, so we go for the equation 1. So we substitute the dimensionless parameter here. Then we found that after we factorize all the things, so we found that there are no extra parameter comes out. So mean there are no parameter appearing, means there are no dimensionless parameter could be related to continuity equation. So, and then this is the equation number 2. So we have 2 terms. Normally, I will solve part by part. So let's say we solve the left-hand side. So we substitute the dimensionless parameter here. So we get this one. So, and then for the right-hand side, so we substitute the dimensionless parameter. This is the nodes to get the value of d square del square u over del x square, and finally we will get this term, and this is the del square u over del y square, and we get this term. So I think I already discussed about this in the tutorial. So the trick is here. So for example, we have the x star equal x over x, and then we have the del over del x star. So we substitute the x star as x over x, and then we could neglect the value of dx here. So we will have x 1 over L. So and then we substitute it here in 1 over L, so we will get this term. So I hope you could do this at home. So and then we substitute in the term, so we get this one. So and then we rearrange the final equation. So we divide all term with v square over L cube. So we will have this term. So and then if we compare with the original terms, we will find that we could get this term, an extra terms here. So and then we found that this term actually can be simplified as a Grashof numbers. So that is the idea what parameter that you could use to analyze your situation. Okay, the problem is from where the word Grashof number and so on and so forth comes on. So comes from. So I think nowadays, okay, there is a lot of dimensionless number you could get from textbooks, you could get from the journal that you read. Okay, so but let's say you are doing this 100 years ago. So that's why maybe, for example, in this situation, a researcher named Grashof do the things, do the dimensionless analysis like this, and finally he get the terms like this one. And then because this term is, nobody used this term previously, so he named this term as Grashof number. So why we say it just a number? Because there contains no units. Means that if you are doing your research and then you do the dimensionless parameter, you have possibility to get the novelty from your research by searching the dimensionless number. There is still a few dimensionless number that can be produced. For example, in the last 5 years, I think there is one Malaysian student named Faisal number, I think. I'm not so sure about that, because it's related with the heat transfer. I'm not in heat transfer. So it produced the F numbers and so on. So that dimensionless number is showing certain idea. After, if below certain value, so it reflects certain condition. If exceeding certain value, it's showing certain condition. So means that in doing research, it doesn't mean that you need to try very new things. For example, you need to be the first one who use this mixture and so on and so forth. Sometimes you could get your novelty by having analysis like this. Okay, or so this is one tricks. So another tricks that normally I ask my student to try is by having a log graph. So if you have a log graph here and then you have another log graph here, sometimes a scattered graph, for example, we have a very, unpredictable, difficult to subscribe about that graph. Sometimes it can be at certain style. It's maybe a curve or it's maybe a straight line. Then if it is a straight line, okay, you could get the gradient and maybe that gradient will show you something. So you could see from the experiment or the simulation that you did. So what is the changes of the changes of gradient will give you what kind of phenomenon. So that's the way research student get novelty from their research. Because if every time if you need to get novelty from new things that you produce, it takes a lot of time, or sometimes you don't have a new things. For example, people want to mix nanoparticle and so on and so forth. So you try to produce a new nanoparticle and so on and so forth. So it actually takes time to take a very new types of nanoparticle. So why not you comes out with the chart that help people to ease their calculation, to ease their prediction and so on and so forth. So that's the idea. So one of them is by using the dimensionless analysis. Okay, so we have the equation number 3 here. So we have this equation. So I think you know what to do. We have the dimensionless parameter here. So, and then we substitute. So I think this is the notes how to get the value of dt dy. So for example, we have a dt dx. So we substitute the t here. So it's quite complicated. So and then we already have the x here, and then it's become the L, 1 over L, and so on, and then it could be simplified as this one. So and then we just follow the idea of the dt dx, so the dt dy will become this one. So and then this is the examples to get the value of del square t over del x square. So we have this one. This is the final terms. And then this is the terms for d square t over dy square. So and then we substitute everything in the original equation that we have here. So and then if we go for the left hand side, we get this one. So if we go for the right hand side, so we have this one. So and then if we solve that equation, so we have these terms. So and then you found that there is one extra parameter comes out. So this parameter is this term. So if you could see here, its lay is here. It's k over rho cpv. So if we have this one, so this is a Prandtl number. Okay, that's why in if you read certain journal, So suddenly it's talk about the Prandtl number, about the Nusselt number, and so on and on. So the reason is maybe they do the dimensionless analysis. They will found that that parameter is appear in their dimensional analysis. That's why all the parameter is discussed in terms of Prandtl number. But nowadays, I think you could see the trend. If you do this one and the Q1 or Q2 journal is doing Prandtl number and so on, so you just follow that one. So take note that this is the reason why they use the Prandtl number. They do the dimensionless analysis.